Hello everyone. See, in the last video on based on the magnetic effects of electric current, part 1 and part 2, we studied about the how when we place a magnetic current carrying conductor inside a magnetic field. Let us take this in north pole and the south pole. The field lines are coming from north to south like this. When you place any current carrying conductor in a magnetic field, okay, let us take the current carrying. When we place inside a current carrying conductor, we place it inside a magnetic field, it will undergo some motion, right? That because of this motion, we can see the motor working of motor, right? Because when it will move, we will provide that motion in particular order, so that will make it rotate. So that means mechanical energy will cut. That means by motion of the conductor, we are getting this motion by passing what? By passing electric current. Is this reverse is possible? That means when you move the conductor, okay, we are passing electricity, so that motion of the conductor will come. When you move the conductor, okay, when you're going to move the conductor inside a magnetic field, okay, suppose your magnetic field is north and south pole, let us imagine, okay, from north to south magnetic field is there. In this, is it is possible, okay, that means when you place any conductor, okay, when you're going to change the conductor inside a magnetic field, is the current will going to produce or current will going to induce. So that is what the topic called electromagnetic induction means. So by placing or by changing magnetic field or by changing the conductor position, that means we made the motion of a conductor, so we can able to produce the induced current. So this experiment was done by, first of all, the Michael Faraday, the English scientist, the Michael Faraday, the done experiment, and he proved, okay, the new law, that is what how electromagnetic induction, okay, how you going to induce the current in a circuit by moving a coil. Okay, the moving coil or by changing the magnetic field, okay, we can change the magnetic field or we can move the coil. Based on this, we are going to produce the current. Okay, that is what called induced current. We are going to achieve the induced current by changing this and this, changing magnetic field or by moving the coil, or we can increase the number of turns of the coil, and the turns increase the strength, we are going to induce this induced current. So all this we are going to study in the electromagnetic induction concept of this chapter today. So what is electromagnetic induction? Okay, see, electromagnetic induction refers to generation of electric current. See, before we are passing electric current, generating mechanical energy. Here opposite, when you generate electricity, how you could get electric energy? By passing a metal wire through a magnetic field. So how it is like a north-south pole, the magnetic field is there. Inside a magnetic field, we are passing wire. That means we are moving conductor inside a magnetic field. When you move conductor inside a magnetic field, that time reverse of this, electric current is producing. Okay, induced current is producing. That is what we call generation. So that is nothing but electromagnetic induction. Electromagnetic, okay, electromagnet or magnetic induction is a production of electromotive force across the electrical conductor in changing the magnetic field. When you change the magnetic field, the motor, the coil is going to rotate, because changing magnetic field, coil going to rotate. When coil going to rotate, the current will going to induce, opposite to electric motor. So when an induced current is produced because of voltage production, that is what we call electromotive force, EMF. They'll ask for exams also. What is EMF? Electromotive force. Due to changing magnetic field, it is called electromagnetic induction. When induced current is produced because of EMF due to the changing magnetic field. So this is nothing but electromotive force. Are you clear, children? What is electromotive force means? When changing magnetic field, okay, induced current is produced by changing EMF, electromotive force, because this is what we call electromagnetic induction. So let us see brief study regarding this electromagnetic induction. Yeah. See, electromagnetic induction brief history is actually this electromagnetic induction is given by the Faraday actually. Okay, children. the English scientist called Faraday in 1820, what Astward discovered magnetic field is always associated with electric current. That means suppose your current is there going inside a conductor, right? Astward given that only when current is moving inside a magnetic field, current is moving inside a conductor. Okay, when current is moving inside a conductor, so around this magnetic field will be circulating around this. Okay, this is given by Ashford. So Ashford explained we don't know in electricity when you use the compass was it will show deflection because current is moving out of this, current is producing because moving up current. So this is Ashford given. Again, what in 1831, after 10 years almost, you can see, no? So August 31, Faraday discovered electromagnetic induction by the famous induction ring experiment. So what is this famous induction ring experiment? We'll see that. So now you clear know who discovered and who what. Astro discovered magnetic field will be produced. That means magnetic field and the current are interrelated like this. Okay, when current is moving, not stationary current. Only when the current is moving, that time we can able to produce a magnetic field. And the Faraday discovered based on that when you move the coil, okay, when you move the coil inside the magnetic field, we can able to produce the induced current. So that is given by Faraday. So how what is this law derives that, and I'm going to check, children. Yeah. See, electromagnetic induction test it is made by what he taken simple equipments, try to understand this. Okay, just a second. You are taken, make a connection between galvanometer and the copper coil and the electrical wires. So you don't know what is galvanometer. If the galvanometer show just deflection, children. So galvanometer is the instrument, it will show just a deflection. Which direction current is moving, in that direction, like this instrument galvanometer will be. It is a round thing, it will contain the deflection here. Which direction current is moving, that direction that shows the deflection. Okay, current is present or not and which direction is moving, we can detect using the galvanometer. Okay, children. So here see ammeter the given, that means current we can measure, or we can show take galvanometer also, and we take a coil. Okay, some coil is wound around the copper rod. So this a coil is there. When you bring the bar magnet means what? It will continuously emitting field of lines, right, children? Because the field of lines is coming from the bar magnet. When you brought this bar magnet, okay, near to this coil, at that time you can see the deflection in the galvanometer. See the when you brought nearby, you can see the deflection. Okay, or else when you change the polarity, if you bring the south pole, that time you can see deflection in the opposite direction. When you move the magnetic field, magnetic move nothing but what is we are doing, changing. What we are changing, children? We changing your magnetic field. When you change the magnetic field, the deflection will be shown in the galvanometer, right? And when you not change, you fix this magnet also and you fix the coil also, there is no deflection. You can observe here no deflection, it will be at the middle only. When you bring nearer, so see that when you bring the north pole nearer, at that time it will show deflection. When you bring the again you bring outward, when you bring towards, shows deflection this side. When you bring outward, again it will show deflection opposite side. So that means it is showing the deflection when we changing the magnetic field. Try to push the bar inside the coil and take away from the bar from the coil, so that time you can see this kind of deflections, right, children? This is the experiment done by the experiment is done by Faraday. So what this experiment, inference of this experiment is that, children, so what it says that when this ammeter will show deflection, when current is induced in this coil, then only it will show deflection, because we not connected a coil. See what is this, just a coil is there. Okay, the color. Just we taken one coil, that's all. Okay, the coil is connected to two ends of the galvanometer. Galvanometer is not a source to provide any current. It's just an instrument will show where the current is moving in a coil, it will show deflection. Okay, inside this like a needle only, it will show deflection. You can take galvanometer, I can use ammeter also here to show the deflection. So when you brought magnet, okay, north and south part, both the coil, okay, and the magnet are at rest, no deflection in the coil. There is no any deflection. If you bring magnet approaching towards like this, when your magnet is being very nearer to the coil, try to immerse into the coil, that time you can see the deflection. That means when you brought here magnetic field, we are changing. When you change the magnetic field, induced current will be induced in the coil, so that it will show deflection. Again, you taking out also, again you changing magnetic field, right? When taking out or going in the changing magnetic field of Lenz, so that again it will galvanometer show deflection. That means again current will be induced. That means when there is a change in magnetic field, flux what we call, then that time the induced current will be induced in the coil. That is proved this experiment. I hope this is clear, children. Yeah. So characteristics of electromagnetic induction, let us see what are the characteristics of this. Is first one, for movement between the magnetic bar and the conductor, there will be deflection in the galvanometer. When there is a movement, okay, when there is a movement, so whether going inward or outward, that time you can see deflections in the galvanometer. If a bar and a conductor remains a steady state, they are not moving. When they both are at the coil and the bar both are at rest position, galvanometer does not show any deflection. It will be straight. Even it is moving, okay, when it is moving, okay, that the coil is moving and magnetic field is moving, that time it will show deflection. So if the pole of a bar magnet is changing, the direction of induced current will be changed. The pole, if you place initially north and south pole, it will show like this deflection. If you place now south and north pole, okay, if you change the poles of a magnet, that time what will happen? The deflection will show opposite end. Okay, children, that is next. When a current is induced in the coil, okay, when the loops in the coil increases, that means number of loops are going to increases, the deflection becomes greater. That means initially it is showing only this much, means it will show more deflection. That means more strength will be there, so more greater will be the deflection. And when the loops are decreases, becomes a smaller deflection. Loops are decreases, again it will come back to same position with a smaller deflection. We need to observe. That means strength of current depends upon number of loops also, and the direction of and position of magnets, and the direction of magnetic field also. Clear, children? I hope this slide is clear to you. See, Faraday experiments on induced current. Faraday conducted 3 different experiments to find the electromagnetic induction. For that, he used the coil of wire, galvanometer, bar magnet. By noticing deflection, he conducted the first experiment. Okay, he conducted all these experiments. See, first experiment he replaced the bar magnet with the current carrying solenoid. I think in the first concept, in part 1, we understood what is solenoid, right, children? When we pass electric current through the solenoid, what happens? It will be act like a just bar magnet, right? One south will act like a north. Another second. When you pass current through the solenoid means it is a spring. When you pass current to the spring, this end which is connected to negative terminal act like a north pole, and which is connected to positive terminal, that will be act like a south pole, like a bar magnet. Imagine this will be acting like now bar magnet. How bar magnet emitting the lines of force, no? Like that only here also the lines of force will emitted from the north pole, and the south pole all the lines will come to merge. Right, children? This is what we are going to observe. Okay, this is what electromagnetic Faraday's experiment. First one. So what he replaced, instead of just one coil, one circular ring, and a passing current inside and outside, he replaced with a solenoid like this. And he placed the 2 coils close together, face to face. Like this, 2 coils are going to face like this he placed. But at rest, they are at a rest position now. So with respect to each other, so that means with respect to A and B, the A and B are not moving. With respect to this is at rest, and with respect to this is both are at rest position. With respect to each other, by closing and opening the circuit, he conducted the third experiment. That means by closing the circuit, that means using the switch. He can close the switch and he can open the switch. That time he conducted the experiment. So he totally conducted how many experiments? 3 experiments. One using the just coils, and second one he used the instead of magnet he replaced the solenoid, and the third case he replaced the coil. He used the 2 coils, one with respect to other, and he conducted with the source and other he taken a galvanometer. That means, see in the part A, what is taken in the A, there is no current. Okay, only coil B be passing the current. Because current in the B, it will going to induce to current A. How? So he is going to explain in the third experiment. I hope this is clear, children. Next one, magnetic flux. See children, what is this magnetic flux? Indicates the flux of a magnetic field through the, just a second, I'll take a pen. Magnetic field flux or a field through the surface is defined as similar manner as we define flux of electric field. Magnetic field or flux, both are same, is a constant magnetic flux passing through the surface. Okay, when we have like this, I will just imagine children, you have one area. Okay, per unit area, let us take the surface area, we can take it as a F's, and a magnetic field of lines. They are going B. How many magnetic lines of force will pass per unit area? Okay, that is what we can call it as a flux. Okay, number of field lines will be passing through an unit surface area, this one. So if it is passing parallel, at what angle they will pass? If they are passing perpendicularly, more. If they suppose the magnetic field is like this, if you place the coil like this, you can observe here very few number will be going with some angle you place, or else you place almost vertically. Suppose field lines are like this, if you place your coil horizontally, you can see the zero lines are passing through this. Okay, passing means suppose you take one line like this horizontally. Okay, number of lines will come and hit here. If more number of lines when you place perpendicularly. If you place horizontally, right children, like this, where's the number of lines? Number of lines are passing above and below, they're not crossing the unit area. That means flux will be zero when you place parallel. When you place goes on increasing angle, if you place, number of lines going inside will be maximum. Okay, so like that we are going to represent the electric flux and magnetic flux also. So given by the formula pi b, we can get magnetic flux, call it as pi b is equals to b magnetic field into surface area into cos theta. Okay, this is given by formula of magnetic flux. I hope this is clear, children. Yes, the next one, magnetic flux definition. See, magnetic flux is usually measured with the fluximeter. It contains a measuring coil and electronics that evaluates changing voltage, measuring the coils and calculate the magnetic flux. Okay, advanced level you're going to learn all this. SI unit of magnetic flux is Weber. Remember, some exams they might ask this, and it derived like voltmeters. Okay, volt per second. RCGS unit is Maxwell. Okay, remember SI unit is Weber and the CGS unit is Maxwell. This is again scientist name Maxwell given. No, that's what we call Maxwell and the Weber are the 2 units of magnetic flux. 5B. Clear, children? Laws of electromagnetic induction. The Faraday given few laws of electromagnetic induction to explain is induced current easily. To understand regarding the induced current, you must know this laws. What is the Faraday's first law? Based on activities, we done 3 experiments. Based on inference, you given this laws. First law suggested electromagnetic induction, that's what you call electromotive force, EMF, induced in a wire is proportional to the rate of rate of the flux through the coil. So EMF produced in the coil is proportional to rate of change of flux. Okay, this is the first law he given. And the second, Newman law means the magnitude of induced EMF. That means the magnitude of induced EMF is proportional to rate of change of magnetic flux linking to the coil. It is equals to rate of change of flux linking to the coil. And the Lenz's law, Lenz's what he given law, the induced EMF acts to the current in a direction that opposes the flux and causes the inducement. That means E given minus of E minus of d pi by dt is told. So all these laws, if we go little higher classes, where you're going to understand clearly to solve the problems, these ideas are required. Okay, try to understand those laws. Faraday's law, Newton's law and Lenz's law. So all these things told regarding what? EMF only, how much EMF induced in the coil, that will be, our magnitude of this induced EMF will be proportional to what is the change of flux, the rate of change of flux in the opposite direction. Okay, when rate of change of flux happening in this direction, in the opposite direction, the induced EMF going to produce. Clear children, this is regarding the laws of electromagnetic induction given by Faraday, Newman, Lenz. Okay, all these names please remember. Yeah, experiment and Lenz's experiment. What he done in experiment to prove his law is that, okay, this is the laws. See, according to Lenz's law, direction of induced current in a coil in such that it is always opposite to cause of produce. So this is a, let us say, North Pole and South Pole. If you bring one more North Pole here, so that time the induced current, whatever the current induced EMF will produce, that will be opposite to rate of change of flux. And this law follows the law of conservation of energy. Okay, whatever energy is giving you, that will be converted in the form of induced EMF. Okay, this explains law of conservation of energy also. Okay, children. Okay, don't worry if you not understood also, because this is little higher topics to you. If you go little higher classes, no, that time you need to understand all this topic. And the self-inductance, okay, is the characteristics of the coil itself. And self-inductance means it is the characteristics of the coil itself. When the main current in the coil decreases, the induced current opposes and delay the current in the coil. When the main current in the coil increases, the induced current opposes the growth of the current in the coil. Are you understood? Self-inductance means this is self-adjusting. How it is adjusting means when the main current in the coil decreases. Okay, when the current going to decreases, induced current opposes the delay of the current in the coil. Induced current, whatever induced current, that will be delay in the current in the coil. When the main current coil, whatever the main current coming the coil, that will increase means the induced current opposes the growth of the coil, growth of the current in the coil. That means it will just regulate the current. It is not increasing or decreasing. When it is low, it will makes it high, and it will high, that time it will makes it low. So just self-adjusting to balancing point. That is what we call self-inductance in the coil. Clear, children? Yeah, it's all self-inductance. Now we'll see what is the mutual inductance. Okay, self-induction means only one coil we taken, that is adjusting the whatever the current is coming. When it is growth or delay, it will go to adjusting. In whatever the mutual induction means, here taken the two coils, coil 1 and coil 2. In coil 1, we are supplying the electric current, okay, by generating galvanometer. Sorry. Here we are supplying the current actually in the coil 1 by AC supply. In the second coil, we are not supplying the coil, only galvanometer will show the deflection. That means the current coil. When a current is moving in the coil, what happens? It will going to produce a magnetic field. That magnetic field will be passes to the second coil. Okay, this magnetic field will be induced to the second coil. When a change in the coil, magnetic flux in the second coil creates the again induced current will be created here. Because of that induced current, the galvanometer showing the deflection. So how it is seen? When the main current in the coil decreases, okay, when the main current in the coil decreases, so what will happen? Induced current develops in the neighboring coil, okay, opposes the delay in the current. In the self-inductant itself, it is opposing. But here the second coil will opposes the delay in the current. When the main current in the coil increases, main coil, okay, this increases, that time current developed in the neighboring coil opposes the growth of the current. That means again it is also self-regulating. Both the coils will do that work of regulation here. Okay, children, I hope this is clear what is self-induction and the mutual induction, like this. Let us see how the Fleming's right hand works. See, left hand we understood when the current and magnetic field is there, how direction of the motion of a conductor in the left hand we got. Right, children? Fleming's left hand for electric motor we understood that. So for the Fleming's right hand rule, it will give when we change the motion of a conductor. Okay, when we going to change the motion or when we going to apply the force on a conductor or a current carrying conductor. So when we apply motion on a conductor, just motion of a conductor in a magnetic field, so how the current will be produced. So from this to how induced current will be induced in the current will be given by right hand rule. That means when they are perpendicular to each other, the motion of a conductor and the direction of the field are perpendicular to each other, that time the current will be also perpendicular and coming maximum current will be coming. So that is given by Fleming's right hand rule. See children, thumb indicates direction of force. You can observe here, no, the thumb indicates the direction of force. Yeah, here see children, the main finger are we call as a thumb. Okay, thumb is nothing but the thrust. Remember, thrust is a force. The thrust is nothing but force. The force, direction of force of the conductor in upward direction, here thumb, okay? And the forefinger indicates the direction of the field, magnetic field. In both the cases, it is magnetic field only. And when these two are perpendicular to each other, when we apply force in a conductor, that time you will see induced current will be perpendicular to this two, okay? Perpendicular to this and also perpendicular to this also. It will be like that, induced current will be induced. So this induced current direction is given by Fleming's right hand rule. So direction of motion of a conductor given by left hand, and this is given by Fleming's right hand rule. I hope this is clear, children. Yes. Yeah. So using the Fleming's right hand rule, we are going to understand the important, that is electric generator, how it will work. Yes, children. See, based on electromagnetic induction using the Fleming's right hand rule, how we can tell this electric generator will work. So this is the electric generator. It will be works with, see, in the AC motor, that is electric motors, we just by passing electricity, the motor is rotating so that we are getting work from that. Now we are rotating this coil, okay? By using external force, we are giving the force to the coil, okay? By producing the force in the coil, that means by rotating the coil, we in the magnetic field, okay? Magnetic field is the same, it is coming north, so whatever the magnetic, in the magnetic field we are going to rotate the coil. That means when changing the motion of a conductor, okay, the direction of or motion of a conductor we are going to producing by applying external force, so that what will happen, the current will be induced. You can see no galvanometer deflection, the current will be induced like this only. Whatever your generators in your home, how they will work when electric current gone, so that time how the generators are working in your home, okay? Battery generator, they will be work because of this. When the motion of a conductor is going to change, because of this motion of the conductor, generator going to work. That means the electric current going to generate using the by passing mechanical energy. That means from mechanical energy we are getting electrical energy, that is here actually called induced electric current we will get by producing, by passing electric magnetic effect. So how it will be work? So again use of Fleming's here right hand rule you are going to use. This thumb indicates the direction of motion what you are producing in the conductor. The forefinger again indicates the direction of field only, and the in thumb middle finger indicates the direction of current, or we call central finger indicates the direction of the current, induced current, which correct direction induced current will be inducing. So let us see or analyze the two at a time. So left hand and right hand, both the four fingers will indicate magnetic field only, so no confusion in the four fingers. You can take the central finger here in the left hand, it will be current what we are passing, okay? Current what we are passing, here current what we are getting, that is induced current. And here motion of a conductor will be happening, here we are giving motion to the conductor, right children? This is regarding left hand and the right hand in the conductor. I hope this is clear to everyone. You can see the working principle of a electric motor. Clear children? You can see the working principle of electric motor is, see, This is work on the principle of generator, works on the Faraday's laws of electromagnetic induction. When a coil is rotated in a magnetic field by some mechanical means, we are producing some mechanical means, we can rotate it, magnetic flux is changed. Okay, because of change in magnetic flux through the coil, according to your Lenz's law, when change of current, okay, magnetic flux will change, EMF will be induced in the coil. So because of induced EMF, we get induced current. Okay, this is the principle and working of the electric generator. I hope this is clear to everyone, children. Yes, children. So this is what were in the entire chapter we learned. Okay, the last one topic is pending, that is regarding the domestic electrical circuits. So how it will work and what is the problems based on that concept we're going to explain in upcoming videos. Okay, children. Thanks for watching. Keep watching like this and try to share your friends. Let them help for the exams. Okay, children. Thanks for watching. Please like and subscribe and put on the bell icon button, press on it, so that whenever I do videos on NEET and JEE problems, it will get notification to you. So these videos are just basics to you. I'll do more videos on IT JEE problems, so that will be helpful and gives a practice for you. Okay, children, keep on watching my videos. Thanks for your. Bye, children.